Okay, let's get started. Welcome to everyone in the room and to the people online. I'm Petra Ylitalo from Novia University of Applied Sciences in Vaasa. And Novia is the EU lead part in OFFwind. OFFwind offshore wind turbine farms is an Interreg Aurora project that started in October 2022 and ends now in October 2025. Some basic facts: we are in the priority area smart and sustainable growth within the Interreg Aurora program. The specific objective is smart specialization, research and innovation. The total project budget is 1,374,000 euros. As all the other Interreg Aurora projects, we contribute to UN Sustainable Development Goals. We contribute to affordable and clean energy and to climate action. So about goals and aims of the project, the overall objective of the OFFwind project was to boost the uptake of offshore wind energy in the Aurora area by overcoming the Arctic challenges. And we have reached this by working on the aims in the second paragraph. We have to provide solutions through case studies to the limiting Arctic challenges caused by harsh weather conditions, ice, wind, waves, snow, by developing methods and models to reduce the effect of these. De-icing methods, ice mechanical models for ice structural interaction and dimensioning criteria, assessing wind and wave forces and loads, seabed condition and access to farms and use of zero carbon emitting building materials. We are a consortium that provides complementary skills to the project. Luleå Technical University comes with concrete technology knowledge. SINTEF with knowledge about ice condition, ice mechanical and ice structural interaction. Novia with icing and de-icing knowledge, and Tampere University with surface modification and coatings as expertise. We have met on many times online for monthly meetings and also a yearly meetup in person. Here is picture when we met in Vaasa 2023. And in Luleå in 2024. We have also made some very valuable excursions. First to the wind farm site in Korsnäs, the whole team, in 2023. Also a smaller team have done ice measurements on the wind farm site in Korsnäs 2024. We also visiting High Water Bridge construction site in 2024. This is in our region, and we got some good view on how to construct and build in marine and cold climate. And then over to today's seminar. The aim of this seminar is we want to present the team and to give the participants some insight to our cross-border team and to our joint research. There is much more to read and discover on our webpage. So please visit offwindproject.com and go to publication. I will now give the word over to Johan Wasberg next, and then also to Bjørnar Sand and Magdalena and Heli. So yeah, welcome to the stage, Johan. Thank you.
Okay, thank you. Hope everybody can hear me. And so why do we think about wind power in the north of Europe with all the challenges? Well, the main answer to this question is, of course, great potential. If we look at the bottom points here, the present use of electricity in Norway, Sweden, and Finland. We have Sweden the biggest and 170, Finland 80 terawatt hours, Norway 127, totally 377 terawatt hours. I think these are 23 figures. Okay, some wind power goals in Norway. They are looking at 140 terawatt hours offshore by 2040. And if we look at the only 10 projects in the outside Gävle, basically in Sweden, they have similar capacity, an additional from just 10 projects, 122 terawatt hours. And in Finland, we have 24 ongoing offshore projects in progress, over 40,000 megawatts and about 160 terawatt hours. So this potential is these three it's over 400. So that is like more than the present total consumption in these three Nordic countries. This we see the Interreg Aurora area, colored to the bottom right, and we have like the Sea and Gulf of Bothnia, Northern Baltic Sea, and we have the Norwegian coast, of course, interesting for wind power. These are the Norwegian to the left areas, and we have a case study, Nordwind 4D in Norway. Floating wind power, it is of the four on the top is the lefting, and here on the center map we can see in yellow the 10 Swedish projects I will refer to further, and then as we see on the right map, we have a lot of ongoing interesting areas in the Gulf Sea and of Bothnia, and the Korsnäs case study area is marked with the red arrow. Interesting when we look at these 10 yellow parks in Sweden and one very far north in Polargrundet in the North Bay of Bothnia. Then interesting is the depth, which is between 18 and it's up to 80. But that means basically to summarize that inside the Baltic, the Bothnia Gulf and Sea, it's suited for bottom fixed turbines. And then when we look at the Atlantic coast, that would be mainly floating, as in the Norwegian case study. This is from the environmental impact assessment plan for a program from the Korsnäs area, the Forststyrelsen and Vattenfall. So this is basically you have a park, you have the turbines in the sea, bottom fixed one way or the other, a sea power station, converter station, then you have a cable to the shore, and then another converter station, and then you have connection to the national grid. This is in general. Now in Vasa, where I come from, ABB makes subsea power station, then transformers, subsea transformers. So that is also one alternative. It does not have to be above the sea level. It can be also submarine transformer. We have Korsnäs. I think Korsnäs case, Vattenfall Metsähallitus Forststyrelsen is quite representative for a park in the sea of the Baltic. We see here it's offshore turbines and then two alternatives for cables. Then the onshore connection will be to the power station in north where the airport is there, around 50 kilometers and considerably distance to Åbacka and Kristinestad in the south, 80 kilometers. So one central factor in the feasibility of the park is, of course, who pays for the grid connection. In this case, because we don't have the stable grid near to the sea in most places, so it's a considerable cost. Here is just what I said. There will be 50 to 85 kilometers onshore connection, which is not free. This is an example of the Korsnäs layout from the EIA program, and then the three-phase cables, most likely to be used for submarine cables to be used in the transmission inside the park to the substations. Some facts of the Korsnäs park, I think it's quite large, but I think this is a representative examples of the park in ongoing in the project in the Sea and Gulf of Bothnia, also quite similar to the Swedish parks in many ways. 15, 30 kilometers from the coast and quite good wind speed, 9.3 to 10, and then the stated in the program max capacity is 25 megawatts. And talking in the parks now, I have looked at the turbine size is between 15 and 20 up to 25 is the capacity. So that means that it's an evolving industry. Every new turbine size is basically a prototype with some surprises, and they're not so easy to predict and so on. So and then the height is many times between 300 and 400 meters. And I was talking to the experts some years ago, and they said that we don't fully know what happens in the air so high. There could be some low-level jet streams and so on. And in the west coast in Vaasa, we have had 2 rotor blades have broken, and it is very high and very strong powers. So we see here. Okay, challenges. Then of course icing. We will hear about that both on turbine rotors and pack ice and drift ice and ice damage on submarine cables on ground waters, remote locations, accessibility, maintenance problems, long distances to the connection points. And we have in north-south in all these 3 countries, we have limited power transmission capacity. People in the south and much of the generation in the north, salty, challenging environment, and as I said, an evolving, developing industry. There is no mass production. It's more on the level of prototypes. So, and the cost of generation of this electricity is not the cheapest, but there is a lot of challenges, and I think collaboration is needed to solve all these challenges between industry, public, between different institutions with specific competence and to overcome these challenges. We have to the left seen a dramatic drop in the solar PV sector due to mass production in millions. Also offshore power and onshore power, wind power has dropped, and there are predictions about the future offshore costs, and summarized in the table to the right. If we look at 2050, this is the mid scenario. A fixed bottom offshore park predicted to reach 72 around euros per megawatt, but equal 7 cents, and then the floating will always, I think, be more expensive. So in the optimistic case, they could go down to 6 cents, but predicting the future is very difficult. So we have, and you see the gap between the orange top line for conservative predictions for floating and the fully drawn green line there is that's the most optimistic and pessimistic scenario for floating, and it's a big gap. It's very difficult to predict. Thank you.
Hello, my name is Bjørnar Sand, and I'm going to present preliminary environmental and technical feasibility study of offshore wind turbines in ice-infested waters. An offshore wind park is located in the cold region marine environments with seasonal and dynamic ice condition. This is an early phase development of offshore wind park. So full implementation is not considered in this project. So the primary objective is to understand the environmental load, ice and wet ocean pre-assessment, evaluate the technical feasibility of gravity-based foundations for wind turbines in ice-infested waters, and to develop a general framework for ice wet ocean pre-assessment and feasibility study assessment of gravity-based foundations. As case study, we have looked at the Korsnes wind farm area outside Vasa off the coast of Finnish west coast. So we have already gone through some of this. For the environmental study, we have used the total 4 weather stations and 2 buoys in the sea. And we have used the temperature data for estimating ice thickness, marine weather observation, wind speed, wind gust speed, wind speed and directions, wave height, wave periods, and wave directions. So for estimating ice thickness, we have used a generalized extreme value analysis, and the objective is to estimate the extreme ice thickness for structural design of offshore wind farms. And source for the data is to use the FMI, weather stations at Korsnes. And results we have derived fitted the general extreme value model for the historical data. And the goal is to find the 50-year return level of ice thickness is equal to 0.8 meters approximately. Characteristics I means a wave condition for Korsnes wind farm area. The level ice is 0.77 meters. Wind speed 21.9 meters, and wind gust is 27.4. And then you have the maximum ice velocity 0.6 meters approximately, wave height 7.6. A maximum wave height, high sea level is 1.44, and minimum height level is -1.3. And we have done some optimization framework for gravity-based foundation in ice-infested waters. The purpose was to find a preliminary feasibility assessment of gravity-based foundations for offshore wind turbines in ice condition. We have used the MATLAB-based optimization platform and focused on geometrical optimization, and the aim is to minimize the concrete volume. And we have used some design criteria for stability and overturning and load capacity, a structural stress limit, combination of eigenloads and environmental loads, and the ballast of the structure. And stability is done in the ultimate limit state using partial factors for load and soil properties. Here's the conceptual design for the area is based on the 23 megawatt reference wind turbine. The water depth is 30 meters. Seabed properties is dense sandy moraine, and use DNV standards for the design. The key load values is thrust force acting on the hub, and wind pressure, and levelized force, and ice winds forces. And the power, the rotor diameter is 283 meters. Tower diameter at the top is 6 meters. Tower base diameter is 10 meters. Bottom depth is 30 meters. And here's the final conceptual design for gravity-based concrete foundation. This consists of a cylindrical top section, 15 meters height, and then the transition section between the top cylinder and the conical part. The total height is the conical section is 19.5 meters, and the bottom diameter is approximately 27 meters, and the base plate is 37.2 meters. And we have done some non-linear finite element analysis of ice structure interaction. We have considered the structural dynamics, hydrodynamics, aerodynamics, and ice structure dynamics, and included the structural foundation dynamics using a simplified spring model. Yeah, so the numerical result for ice speed equal to 0.25 meters. The maximum horizontal force is 3 point. No, the mechanical properties of the ice sheet were characterized by uniaxial compressive strength of 3.7 in horizontal direction and 6.7 in vertical direction, and the maximum global load in the horizontal direction is 9.47 meganewtons, with the average of 3.54 meganewtons. And you can see that the iso forces is extremely dynamic. And the figure also shows a snapshot of the ice failure rubble formation at the end of the analysis. So you can see that the ice rubble accumulates in front of the foundation. Thank you. So the next is Magdalena.
Hello everyone, my name is Magdalena Rajczakowska and I'm a researcher at Novia University of Technology. I work with concrete, so in this project together with Andrzej Twiżeń, also from LTU, and colleagues from this project, we try to look at the low carbon concrete technology for the offshore. And firstly, why do we even look into this? Because so far you could see that the prices of the offshore wind energy are quite high. They're predicted to be lower in the next years, but still there's a lot of uncertainty. But the question is, could we lower the price, for instance, if we considered the CO2 emissions price that is related to the materials used in offshore? And here we can make use of concrete. So if we look at the numbers, then
around 79 and 70% of the total CO2 emissions of onshore and offshore are related to the extraction and production of materials. That's of course not only concrete, it's mainly steel, but still in volume concrete is a large part of those constructions. Foundation, which is often made of concrete, contributes to up to 30% of the total CO2 emissions in case of offshore foundations. So if we look at this, concrete is the most used material in offshore wind foundations. And because of the Portland cement production, and Portland cement is still the main binder used in concrete, it produces a lot of CO2 because of the clinkering process. So what can we do to decrease those CO2 emissions? We can use, for instance, alternative binders, but there are other aspects than just replacing cement that we should take into account when we look at the offshore wind structures. So here in this picture, you can see what concrete has to endure when it is placed in environment like Arctic offshore structures. So it is subjected to several different actions from the seawater, from the atmosphere, the freeze and thaw cycles, and also the ice abrasion. So if we consider those difficult conditions that it has to act in, then durability of this material is one of the main parameters. So usually for those who work with concrete, we talk about strength a lot, but durability is a key factor, especially in conditions like this. And when we consider new types of binders, the ones that we are not used to so much yet, that are coming from the waste that would decrease the carbon footprint of concrete, we still have a lot of challenges when it comes to accepting them, even if they're behaving very well in this kind of conditions. And then another question, so what we tried to analyze in this project is how to approach the low carbon concrete in general for the offshore wind. So to be able to help the decision makers to accept low carbon concrete in offshore, for that we need evidence that we can lower the carbon footprint, but in connection to the durability and service life. And to be able to solve this problem, we also need to identify what we need, so what are the gaps and challenges. So within the project, we did several different activities. So we determined the R&D gaps based on the current state of art. We established a modified, simplified LCA framework to be able to include durability and perform calculations for different types of concrete. We also did some lab tests for the durability screening of selected low carbon concrete mixes, taking into account accelerated lab tests and also lab tests with natural seawater captured in the Gulf of Bothnia. And this resulted in a couple of contributions together with our partners from Novia and SINTEF. Some of them are already on the website that Petra showed in the beginning. Some will be published later next month. So here, because the time is short, I will just show the highlights. So regarding the durability framework, as I mentioned, majority of LCA calculations that you can find in literature, they still focus on the cradle to gate approach. So what we wanted to do here is to try to make like a very simple parameter that we can assess different low carbon solutions for offshore concrete foundation, including the durability parameters that we need in this case. So the freeze and thaw performance and chloride resistance, and also strength, taking into account different scenarios with different weights to see how those materials, what are the results of their carbon emissions in those situations. And here we not only took evidence for the mixes typically analyzed, which are with replacement of cement with supplementary cementitious materials. We compare them also with ultra high performance concrete, which has very good durability parameters, but also some other types of solutions which we are working on, for instance, involving hybrid material consisting of UHPC and low carbon concrete with high SEM replacement to see how their results look like when it comes to carbon emissions. So if we look at the comparison, this is just one of the results. So if we compare the typical analysis with cradle to gate from the extraction of materials, we can see that UHPC, because of the high amount of cement, is the highest when it comes to CO2 emissions. Then the SEM and the hybrid mix are the lowest. On the other hand, if we take into account the durability parameters with different scenarios that are input there with the cases that we studied that I showed you before, we can see that those differences are not so high between those different mixes, but the hybrid mix performed the best when it comes to the carbon footprint. If we look at the highlights from the laboratory test, where we tested the different low carbon mixes with volcanic ashes and slag together with Novia, we can see that actually the low carbon concrete in some cases presented better behavior than reference mix, which gives possibilities to study this further. With the test with the water from Belpopofnia, because of the low salinity, the effects were even lower than with accelerated tests. Actually, we observed the increase in strength after 1 year. So we are still looking deeper into the microstructure to understand it better. So to look at the whole system of the offshore structures, if we consider concrete, it's actually not such a small part, and it can give us substantial savings if we look at the numbers here that are calculated for the case that Bjørnar showed earlier, and taking into account our LCE calculation. With the increasing carbon prices in the future, we can actually predict that the impact from the CO2 decrease by the low carbon concrete can be even higher. So it can have a positive effect on the whole acceptance of those kind of structures. So we also established some additional challenges and potentially interesting topics to study. I will refer you to our report for not to waste too much time. But in general, to conclude this part, I wanted to say that from the numbers that we have seen, the low carbon concrete for offshore is promising, but it requires more durability evidence, especially in the pilot in real conditions. And LCA must include service life and real exposure conditions to be able to guide decisions, and collaborations like we had in OFFwind project are definitely necessary to push this topic further. Thank you.
Hello, I'm Heli Koivuluoto from Tampere University, and I'm here as Associate Professor and leading Coating Technologies Research Group. And now continuing this material development part, what Magdalena showed, but now we are focusing on coatings. So how to apply more protection on these structures. And as we have heard already here that there is challenges, and especially when we are dealing with the seawater condition. So we should consider that how we can find protection and like solutions to tackle these challenges. And if we think about the cold seawater conditions, so we have the seawater itself, corrosion coming from there, but then this freezing, thorn cracking and ice impact. So that the cold condition can give additional challenges. And why this is important to study these and understand these challenges is that how we can improve this lifetime, and because we have a large structures, these concrete parts there, how to improve their lifetime, and also this way to get cost reduction and reducing maintenance and other costs related to these problems in marine structures. But then where we have focused on here, Tampere University, is to find new coating technology to protect these concrete materials. And for that, we have studied, and during this project started to work on using thermal spray, which is coating production technology, to produce coatings on these different structures. Why we select this technology is because it's a very well-known technology in industry, and it can be industrially used. There is wide range of coatings and substrate materials which can be used, high coating production rate, efficient, and of course we can get also good coating properties. And one further benefit is that we can produce coatings on large surfaces, which we are dealing here also with these wind turbine foundations. And it's a process where we have a feedstock material, that what we want to have as a coating. It can be in the form of powder or wire. And then we have heat source, so we are melting that material, and then we are accelerating that towards the surface where we want to build up the coating. And then these molten particles, they are hitting the surface, they are impacting and start to build up the coating. And it's fast process. And we have good experimental facilities here to do these coatings. And it can be produced on different type of surfaces, so here different geometries also. And that's why we consider this technology, because of these benefits, to use on these concrete materials. But as mentioned, that these cold conditions, they are also bringing new challenges. So these icing conditions are challenging. So these coatings, they have already shown isotopic properties. So this way we can also get the isotopic solutions on the surfaces. And this is just showing that the technology itself, it can be used on different kind of purposes and different forms. Or then there is also paints and other hybrid materials, more typical ones, what has been used, but then we can go with these thermal spray coatings. So we can get this protection from ice with these coatings, but also other barrier properties, so combining these. And in this project has been developed a multi-layer structure coating system to get this protection. So if we think about this concrete as a substrate material, then we add a bond layer, in this case is electric arc spread zinc coating, which gives also that corrosion protection, what is needed there in the seawater condition. Then we can apply on that top layer, which is flame spray polyethylene coating here, and we can get this kind of multi-layer structure, which has multifunctional properties here. And there is one publication and open access proceeding paper related to these coatings found, which was presented in EWIC conference, and this was collaboration with the LTU. And then also, if we think about these solutions and these multi-layer structures, there is other options as well. So we can have these thermal spray coatings there as these protective layers, and then top layer, in this case it's polymeric material on the top, you can see in that video, so nicely covering the surface. And this way we have other way to protect this surface and also get this like a function in these seawater conditions. And there is also conference paper published in International Thermal Spray Conference where we have focused on this. So during this project, we have developed different material systems, coating system to give a multifunctional protection on these concrete materials. And using this industrial technology, but it was like first time to use that on concrete material, and it has needed quite much development work, and but now we have seen this potential. And of course, because we are dealing with that kind of environment where we have different kind of challenges, of course, testing is also important there. And we have also focused on development of this icing testing to be closer to like showing these requirements from the conditions. And this seawater icing is something needed on a testing system, and that has been developed in this project. And because these coating systems have shown their potential, we are continuing this work after this project. So it's not ready work yet in this sense, but showing good results and promises that it's definitely something that we should continue, and in collaboration with others like this material development together, but and also connect this modeling part there to find these best solutions, and in future make these protective multi-material systems in this field. But yeah, thank you. Yes.
It's Bjørnar Sand again. I will present some from some more work we have done. We have looked at different types of foundation for offshore wind turbines for water level below 60 meters. The bottom fixed foundations is feasible. We have monopile structure, gravity-based structure, multiple foundation, jacket or lattice foundation, and suction control. And for deeper water, we need to use floating foundation. This is examples are tensile leg platforms, barboy, and semi-submersible. And here we have looked into a model for offshore wind turbines that identifies the applied loads and the system response. The external loads are caused by wind, waves, current. Ice load becomes an important factor in ice-infested waters. And ice-induced vibration may lead to fatigue failures of offshore wind turbine structures. For numerical modeling, we can divide into the following categories: is structural dynamics, hydrodynamics, so it's fluid and structure interaction, aerodynamic, is the thrust force on the turbine and wind forces acting on the tower, and ice structure dynamics, and then at last is the structure foundation dynamics. And we have done some case study for a floating wind turbine farm, and Novia. This is it's a 15 megawatt wind turbines, 100 wind turbines floating, and the turbine area is 700 square kilometers. A high voltage DC converter station floating, and 100 AC array cables to offshore converter station, one DC electric cable to land station, and a land station, and a connection to the national power grids. 1500 megawatts in the electric power production, and yearly production is 6.5 terawatts hour. And technology improvement for offshore wind turbine for this Novia Wind deep case. To reduce the level cost of energy, capex and opex, technology improvement can lower the costs, and involves low carbon concrete, improve the surface production system, zero production of substructure, larger turbine structures in zero production, more effective mooring systems, more effective installation, improved array cables, and improved high voltage DC cables, and increased operational service life. 50 years approximately. And then yours.
Okay, just some summarizing comments from me then. Thank you to the team for your presentations. And yeah, what's our next step now when OFFwind is ending this month? We will definitely continue our cooperation, and we have plenty, like several ideas on how to continue working together. We're working on a clustering project with a project in the Interreg Northern Periphery and Arctic program, and the focus in this project is on low carbon concrete solution in cold climate. So, and besides that, we are working on ideas for horizon calls, especially regarding OFFwind, and also with ideas on national and Nordic projects around drones, surveillance, and defense in cold climate. So if you want to discuss or be involved in our research in the future, please feel free to contact us. We are really interested in any kind of business operation in cold climate to discuss that with you. So thank you for attending this, and yes, now you can ask questions.